Okay, folks, we're back. We are still in a little bit of section 14.2 here, and I just left my marker over here. Again, nothing but the most professional videos here. One thing I was looking at the slides, and I didn't really talk about it too much, is on slide number 5. This is just kind of interesting. KW is 1.0 times 10 to the minus 14th. But that's only at 25 degrees Celsius. So on that slide, on the slide I have a guy that's not wearing his goggles. That is actually a Nobel Prize chemist named Gilbert N. Lewis, for whom Lewis acids and bases are named, and also for Lewis structures, or did the octet rule, that's him. Right. So on questions 2 and 3, those are just kind of interesting ones that KW is not constant under all conditions. KW is dependent on temperature. So at lower temperatures, it's different than at higher temperatures. It's actually an interesting kind of question. So I'll let you just kind of look at those. I'm not overly concerned with those. All right. This is the last slide for this week, but it contains a ton of information. Also, it contains some information that sort of relates to the second problem set, or subset, from this week. And I didn't really explain it all that well. So I'm going to go through and try to be a little bit more explicit about this one. So we're on, in the notes, we're C, pH related, it's 14.2, 14.3. I may end up breaking this up into 2 videos because they make it kind of long. In fact, I'm going to note the time, 7:48 in the morning. Yep, I've been here for a while. And this one is part of your homework set for the second set, but I didn't explain it very well, so I'm going to go through and just do a couple of examples there. So for strong acids and strong bases, you don't have an equilibrium. So you don't have to do an ice analysis or anything like this. So, for example, so if you pick up a bottle of hydrochloric acid, and it says 0.9718 molar on it, well, the pH is going to be negative log of 0.9718 molar. And this is actually a good example to use. That's really pretty concentrated, and I believe you get 0.012. That's really close to 0. That's super acidic. H2SO4 is diprotic. So actually the concentration of the overall molecule is only half the concentration of the H+. So in this case, the pH is going to be the minus logarithm of 2 times 1.0 molar. Believe it or not, negative pH is possible. I think that ends up being correct. So strong acids, strong bases. I'm not going to memorize a bunch of things. Hydrochloric acid, sulfuric acid, nitric acid, those are pretty common strong acids. And let's see. So for bases, so you grab that bottle. Okay, that's fine. You grab that bottle from the shelf, and what does that mean? Well, this is a strong base. So group 1 metal ion hydroxides tend to be very strong bases. They dissociate completely. So sodium hydroxide, the classic one, potassium hydroxide, lithium hydroxide, all of these are just good to know. So the pH, well, this one, we'd probably want to get a pOH on this one, because that's easier, because this is this. Minus log of 0.0029 molar, and you would get a pOH of 2.5, and pH equals 11.5. Makes sense, it's basic. The pH should be pretty high. And the last one, if you see something like 5.2 times 10 to the minus third, something a little bit more realistic, a little smaller. Incidentally, I'll try to let you know when you're dealing with situations of strong acids and strong bases, since you may not know, like Q's in the problem, something like that. So you grab this one. Well, you get 2 OHs for every one that goes here. So if you want to do the pOH, it's the minus log, well, of 2 times 5.2 times 10 to the minus third molar. Sorry, that's really, really sloppy, but you get the idea. And again, it should be basic, which it is. So just make sure you take that into account. I don't think, oh, some other acids that are strong. Interestingly enough, HF is a weak acid, but HBr, HI, the halogens, those are strong acids. It's kind of interesting. What else? I think barium hydroxide is another strong base. Okay, these are just common ones. What else did I want to give you there? Oh, yeah. All these spectator ions. It says in the notes there, you can write that down. What about these spectator ions? Well, they don't have any acid-base properties. So chloride is neutral. I'm just looking at the notes here. It says cations of strong bases are neutral, anions of strong acids are neutral. Well, okay. What that means is that the spectator ions, the other thing that is, those have no acid-base properties. So chloride, iodide, sulfate, nitrate, all of these do not have any acid-base properties to them. On the other side of the coin, cations are strong bases. So sodium doesn't have any acid-base properties. Potassium doesn't have any acid-base properties. Calcium +2, barium +2. Those do not have acid-base properties. Why do I bring that up? I bring that up because not every aqueous solution has acid-base properties. An example of that. Let's see. So what if you see 0.10 molar NaCl on the side of the bottle, or 0.10 molar CaCl2? And you're asked to determine the pH. Well, what does that mean? these ions have any acid-base properties. This is a cation of a strong base. This is an anion of a strong acid. This is a cation of a strong base. This is these by themselves would not have any acid-base properties. So you wouldn't even do any calculations. If I gave you what is the pH of a blah, 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 blah solution, you would just write down 7 and move on to the next question. So that's pretty straightforward, I think. Okay, sorry, I'm fumbling around with my notes here a little bit. Excellent. I'm going to set up the next part. So we're on number 2 here. So those are non-equilibrium conditions, and that was letter A. Okay, yeah, while we get this erased, you'll also want a table with Ka values, acid dissociation constant, and Kb values. So either a table that I give you, or just reference the back of the book in the 2 appendices for ionization constants for weak acids and weak bases. So make sure you have some of that information in front of you. I'll reference it in the notes. So what is this? This is 2, equilibrium. So let's consider now a true equilibrium. Strong acids and bases are not equilibria. You just take the concentrations and maybe adjust if it's mono or diprotic or basic, and then calculate the pH and the pOH. That's pretty straightforward. But what if you have something that's an equilibrium condition? Okay, I think we've done this one before. Ka and Kb, fine, fine. Yeah, and consult the table in the appendices. So, Ka is the equilibrium constant for an acid. Kb is the equilibrium constant for a base. And they're both really, really small because we're talking about weak acids and weak bases. Yeah, okay. I think we can whip through this. So generically, if you have a generic acid, we just call H because it has to have H, and this A, which is a placeholder for the rest of the molecule. And how do we do? Now with a generic base, we don't want to put an H with it because it accepts the H, so we're just going to use the letter B, just generic. So if we wanted, so we would just write HA plus water in equilibrium with H3O plus and A minus. And for a base, this is just generic equilibrium showing an acid. Bronsted. So Bronsted acid, Bronsted base. The other way around is the base reacting with water to produce HB because it accepts it, plus OH minus. This is generic. It may not always be +1, +1, it might be +2 if that's already a plus. Just keep that in mind. And Ka would be remember, we don't write the water. We don't put the water down here. And this is what you would look up. Tables in your book, there's 2 separate ones. I'm just going to put a couple of them here. So for Oh yeah, I put a couple of examples here. So for HC2H3O2, so that's acetic acid, Ka equals 1.8 times 10 to the minus 5. Just look it up, make sure you can find that. For bicarbonate, this one may take a little bit to find because bicarbonate can be an acid or a base, but make sure you can find this one because you actually find two values listed for this. So for bicarbonate, you'll find Ka is 4.7 times 10 to the minus 11th. And, oh, I mentioned this one before. Hydrofluoric acid, Ka equals 3.5 times 10 to the minus 4. Okay, one that is useful to do here is this Ka is the largest, so this one will be the most, if the concentrations are the same. If they were equal molar concentrations, this would be the most acidic, this would be the second most acidic, this would be the least acidic of these three there, because the Ka is just larger. So if the Ka is larger, it's producing more H+. Most acidic, middle, low, and then N. So just be able to interpret the Ka. The size of the Ka tells you how far to the right that goes, but that's no different than any equilibrium constant. Okay, so just be able to look those numbers up. Fine. For some bases, ammonia, which we could just plug into that formula there, it's Kb is 1.8 times 10 to the minus 5. Interestingly enough, it's the same numerical value. Coincidence. One we're going to use later is called methylamine. Fans of Breaking Bad will know what that molecule refers to. Just a little bad example there. And this is actually called benzylamine. I think that's important for now. Okay, so you want to be able to look these up and interpret them. So which would be, if you had the same molarity solution of these three, which would be the most basic? Which would be the second most basic? Which would be the least basic? Again, same concentration. Weak bases, weak acids, the size of the Ka tells you how far it goes to the right. Similarly for Kb, how far it goes to the right. And that is no different than any other equilibria that we've considered before. We've done this one. This is chapter 13, applied to acids and bases. It's no different. Just be able to access these things. And I think I'm going to stop the video here. This is all really kind of qualitative stuff. And then we'll do some of the actual calculations next video. And I'll just go through a couple calculations involving these. We'll probably end up wrapping up chapter 14. Good job.